This is a long form descriptive based question. So I hope you have read the question carefully. Take your time, read all the keywords, and let's proceed. Here we have a pump which is forcing air into a bottle so that the bottle is launched upwards. Bottle then travels vertically upwards, and then a graph is given for the vertical velocity of the bottle. So here you can see the y-axis is vertical velocity for that bottle. Now the question mentions the bottle reaches its highest point at time t1 on the graph. So t1 is the time when the bottle reaches the maximum height, and then the bottle returns to the ground at a time t2. The bottle then bounces. The motion of the bottle after the bounce is shown as the dotted line. In the part A, we have to find the maximum height of the bottle. Now, how do we find height, which is basically distance? How do you find distance from a velocity time graph? So the principle is area under a velocity time graph gives us displacement. And in this case, the bottle, since it is traveling in a straight line, so distance and displacement will be the same. So all we need to do is find the area under the graph from 0 to t1. Now, let me zoom in this figure. From 0 to t1, you can see the graph first increases and then decreases until it becomes 0. Hence, we need to find the area of this region. So let me shade this region first. So this entire region, area, if you find, that will give us the value of displacement from 0 to t1 seconds. Now, if you observe the value of t1, this is 1.2. So let me write down the coordinates of this point first. This is 1.2 comma 0, and let us try to find the area of this region. So we can approximate this region to be a triangle. Even though it's not an exactly a triangle, this particular part of the graph is a curve. It's not a straight line, but it is approximately a straight line. Hence, we can approximate this region to be a triangle. Now, area of the triangle is half base into height. The base of this triangle is 1.2 and the height of this triangle will be 12. So let's write down the area of this triangle will be half base into height. Base is 1.2 and the height is 12. And if we solve this, we will get 7.2 units as the answer. And what does area under a velocity time graph gives us? That gives us the value of displacement. And if we go back to the question, in the part A, we were supposed to find the maximum height of the bottle that is equal to the area of the graph which we have just found. So maximum height of the bottle will be 7.2 meters. Now, in the part B of the question, we need to identify the acceleration of the bottle when it is at the maximum height. And to find the acceleration from a velocity time graph, the logic is simple. How do we do that? The gradient of a velocity time graph gives us acceleration. And since we are supposed to find the acceleration at the maximum height, which happens at t1 seconds, that means we need to find the value of the gradient of the graph at the point t1. How do we do that? Step number one, we need to draw a tangent at point t1, either using tan theta formula or using the gradient method. So let me explain. Step number one is to draw a tangent at t1. So the tangent will look like this. Now, in order to find the gradient, we need to find the coordinates of the two extremes. So this point coordinate is 1.2 comma 0, and we need to identify the coordinates of this point. Now, in an exam situation, you would need a proper scale, draw a perfect straight line so that you can find the exact coordinates. If your drawing is not accurate enough, then you will get different coordinates, which will decrease the accuracy of your answer. Now, just to explain, let me zoom this picture even more. So let's try to identify the coordinates. So this is about 11.5. So the coordinates of this point will be 0, comma 11.5. And now let us try to find the gradient of the tangent. So first of all, let me write down the coordinates of the 2 points. At the bottom, the coordinates of this point is 1.2 comma 0. So let us write it down, 1.2 comma 0. And on the top, that other extreme, the coordinate is 0 comma 11.5. And now let us use the gradient formula, the y2 minus y1 divided by x2 minus x1. So the gradient will be 0 minus 11.5 divided by 1.2 minus 0. So let's write here 0 minus 11.5 divided by 1.2 minus 0. If we simplify this, we will get negative 11.5 divided by 1.2, which is equal to 9.58. Hence, the gradient of this tangent is 9.58. And let us approximate this value to 9.6. So the gradient will be 9.6. And if we go back to the question, since we were supposed to find the acceleration of the bottle at the maximum height, acceleration is nothing but the gradient of the velocity time graph. And that gradient we have found as 9.6. Hence, we can write down the value of acceleration is 9.6 meter per second square at the maximum height. In this question, we have a uniform beam of total length L, mass M, hinged at one end. So this point is the point about which the ladder is hinged. Now this ladder or beam is acted upon by horizontal force. As you can see, it is acting on the extreme right end. The beam is held stationary at rest. This means the beam is in equilibrium. So we are going to consider both linear equilibrium as well as rotational equilibrium. The beam is making an angle of theta from the horizontal. We need to find the expression for F. And how do we approach questions? Step one is always to draw the free body diagram. So let's proceed. The first force acting on the ladder is already shown. So F acting towards the left hand side. After this, the ladder, of course, has a weight mg acting downwards, and the weight of the beam will act from the center of the beam. And lastly, since the beam is connected to a point which is the hinge, which means the beam is going to experience a hinge force, a hinge reaction. And this is the direction of hinge reaction which will pass from the hinge point. Now, like in the previous case, we can also use step 2, which is linear equilibrium. The net forces acting on the beam should be 0, but that is not going to get us the correct result. But in any case, let us do that. Step number 2, remember, is linear equilibrium, which means that all the forces should cancel each other out. So total upward forces should be equal to total downward forces, and all the forces going to the left hand side should be balanced by all the forces going in the right direction. In this diagram, W is acting along the y-axis, F is acting along the x-axis, but N, the hinge force, is neither along the x-axis nor the y-axis. So we will break the N into two components. So let's say the vertical component is Ny and the horizontal component is Nx. Step 2 was linear equilibrium. So Ny is the only upward force, W is the only downward force. So they need to be equal to each other. So let's write Ny is equal to W. Similarly, the rightward force Nx should be equal to the leftward force F. So we will get Nx equals to F. This is where we are going to get stuck because we need expression for F, which we cannot find because we have two equations and four variables, Nx, Ny, W, and F. That is why, like in the previous question, this step of using linear equilibrium does not help us to get the answer which we require. We needed the value of F. And that is why we will skip step 2 and directly jump to step 3, which is rotational equilibrium. And in rotational equilibrium, the net torque acting on the beam should be 0, and the formula is Rf sine theta. But remember, torques are to be found about a particular point, so we need to establish the point. So as we discussed earlier, whenever we are dealing with hinge forces, we consider the hinge point to be the point about which we are finding the torques. That is why we will find the torques of all the three forces about the hinge point. Let's start with the hinge force because that will be the easiest. Since the hinge force N is passing through the hinge point, that means the torque of the hinge force will be considered as 0. That is simple. Now coming to weight W. Let's find the torque due to W. So the magnitude of force is W. The value of R will be half the length of the beam. Because recall, R means the distance between the point and that point about which the force is acting. So consider the hinge point and this point. The distance between these 2 points will be equal to half of the length of the complete beam. So R will be equal to L by 2. But in any case, let me represent that length. So starting from the hinge point, if I draw a dotted line and going towards the weight, this value will be R. R will be equal to L by 2. And what about theta? Theta stands for the angle between R and the weight. So we need this angle. So if this small angle is mentioned as theta, how do we identify the value of this? So what we'll do, let us create a right angle triangle. I'll extend the dotted line so that this angle is 90 degrees. And now we have a right angle triangle where one angle is theta, the other angle is 90. So this angle, this small little angle will be 90 minus theta, which is what we require for the torque due to W. Let me repeat, the angle between R and W is 90 minus theta. So torque due to W will be equal to L by 2, which is R. The value of F is W. and the angle is 90 minus theta, which we have established. Now, sine 90 minus theta is actually cos theta. So if we simplify this, and also let's put W as equal to mg. So the expression will be L mg cos theta by 2. So W is mg and sine 90 minus theta is cos theta. So this is the expression for torque due to the weight of the beam. This is only the magnitude of the torque due to the weight. Direction is also important. So if you look at the diagram about the hinge point, if we consider the weight has a tendency to move the ladder in a clockwise direction. That is why the torque due to weight will be in a clockwise direction. Now coming to the last force F, which is acting along the x-axis but towards the left-hand side. So it's a horizontal force. The torque due to F will be the magnitude of force is F, which we are supposed to find. R means the distance between the hinge point and the point about which the force is being applied. So basically, we need the distance between the hinge point to this point, which is the rightmost end. So the value of R will actually be equal to the length of the beam. So R will be equal to L, and theta stands for the angle between R and F. Hence, theta is this small little angle where my cursor is currently hovering. So theta is the angle between the applied force and the R value. And how do we find this angle? For that, we will use this angle theta. If this particular angle is theta, so this angle will also be theta. These are alternate angles because this dotted line and the green arrow which we have drawn, they are parallel. If lines are parallel, so this angle and this angle, they will be equal because they are alternate angles. So the angle which we are going to consider for F will be just theta. So the torque due to F will be equal to L is the value of R, F multiplied by sine theta. So it is just LF sine theta, which is the magnitude of torque due to F. Direction is important. So going back to the diagram, F has a tendency of rotating the beam in an anti-clockwise direction. So the torque due to F will be anti-clockwise. And now that's it. We are done. Rotational equilibrium means the net torque should be zero. We have to equate the clockwise and the anti-clockwise torques. So torque due to W should be equal to the torque due to F. So now if we put both these expressions in the equations, we will get this. And since we are supposed to find the expression for F, let us make F as the subject. L sine theta will get cross multiplied in the denominator. So we'll get the expression for F as mg divided by 2 tan theta. So what we have done, we have considered sine upon cos to be tan theta. So F is mg upon 2 tan theta. And if we go back to the question, look at the options. The right answer is option D. So option D is the right answer to this question. Let's do a quick recap of what we have done. Step number 1 is to draw the free body diagram, keeping in mind that hinge reactions always start from the hinge point. Step number 2 is to use linear equilibrium, which means the net force acting should be zero. But in this question also, step number 2 does not help us get the value of F. That is why we skip step 2 and directly go to step 3, which is rotational equilibrium, wherein we will balance the torques. The only catch is we will find the torques about the hinge point, because in that case, the torques of the hinge forces will be equal to zero.